Don't forget to subscribe and ring that bell.
Hello there, the angel from my nightmare. I cannot sleep. I cannot dream tonight. Those are some Blink 182 lyrics. Google them, kids. Recognize. Anyways, I'm excited because we are going to continue the 2023 AP Calculus AB free response questions. And this video, the focus is on free response question number 3. This is the first of 4 questions where we do not get a calculator. Oh, poop. Fiddlesticks, I say. But you know what? It's okay because we're smart. And the math is typically more doable because, hey, we don't get a calculator. And in the Finger Lakes region of Western New York, where I teach in Rochester, New York, it is absolutely beautiful. Okay, normally in May we can get snow, we can get torrential downpours of rain. It could be like almost 90. But today is sunny and 75. It's like San Diego. I mean, you know, of course, it's like San Diego. It's the closest we'll ever get to San Diego today. Sorry, I felt like being stupid, but let's be smart and tackle free response question number 3. Number 3 reads, a bottle of milk is taken out of a refrigerator and placed in a pan of hot water to be warmed. The increasing function m models the temperature of the milk at time t, where m of t is measured in degrees Celsius, and t is the number of minutes since the bottle was placed in the pan. M satisfies the differential equation dm dt equals 1/4 40 minus m. At time t equals 0, the temperature of the milk is 5 degrees Celsius. It can be shown that m of t is less than 40 for all values of t. All right, well, 3a asks, a slope field for the differential equation dm dt is 1/4 times 40 minus m is shown. Sketch the solution curve through the point 0.5. My God, if they ever give you anything like that, be grateful for the free points. All right, well, first of all, in the problem I noticed this, and I'm getting ahead of myself, we're probably going to have to use separable differential equations, which I love to do. And we even have an initial value. When t is 0, my degree is 5. That's an initial condition, so it screams some rigorous work toward the end. But let's focus on 3a. Okay, the point 0.5 is right here. Okay, it is right there. To sketch a solution curve, we just start from that point and follow the kind of lines, kind of like sheep being herded, if you will. So I'm just going to kind of go up. It's going to kind of bend a little bit more, bend a little bit more, and it's going to keep going until it flattens out right there. Guess what? You just earned credit on the AP Calculus AB exam. That is, I mean, that's a gimme. I love that. 3b says, use the tangent line to the graph of m at t equals 0 to approximate m of 2, the temperature of the milk at time t equals 2 minutes. All right, there's really 2 tasks to do here, both very simple. I'm loving question 3 right now, at least for the moment. And let's go, I'm feeling purple here. The line tangent to the graph. Anytime I see that, I immediately think y minus y1 equals my slope m times x minus x1. Once we get this equation, okay, we're going to use it to approximate m of t, which means we have time, which is our x variable, and m of t, or m, which is our y variable. Okay, and we're going to do it when time is 2, so we need this output. All right, but we need the equation of the line first. So I want this line tangent where? At the point where t is 0. So let's not forget, we have t and we have m of t. T is really our x, so when x is 0, Okay, this is helpful because for my equation of a line, I need three pieces of information. I need an x-coordinate and a y-coordinate, which we're going to get here and here. And then I also need slope, and that won't be too difficult at all. But I have the x. It's 0. That's this bad boy right here. They gave us an initial condition. When time is 0, oh, look at that. When time is 0, my m value, which is the temperature, is 5. And let's not forget that t should go in parentheses. So really my y value for my line tangent is 5. So y minus 5. All I got to do is figure out the slope, which is also easy in itself. All right? Slope is the same thing as derivative. Now, if we look in the problem, they give us derivative right here. Notice there's no t in there, only an m. So I'm not going to use my x coordinate, which is my t. I'm going to use my y coordinate, which is my m. All right? So let's say my slope is the same thing as my derivative, dm dt, which is 1/4 times 40 minus m. I want this at the point where my m is 5. So I'm going to take 1/4 times 40 minus 5. That's like 1/4 times 35, which we will lovingly call 35 over 4. This is the derivative or slope that we're using right at the point 0, 5. So let's plug that right in here. 35 over 4. And let's clean this up a little bit because we know we're going to have to solve for m of 2. Right? So this is the equation like this. If you want, you can simplify it a little bit more. I can like add 5 to both sides. And to get y equals. These will go bye-bye. Okay, 35 over 4 times x minus 0. When you have 0, it kind of goes bye-bye. So I have 35 over 4 times x. And then I still have my plus 5 on this side. So this is really going to help us solve for y. Or in this case, solve for m. Now, we want m of 2. I want my m value, which is the same thing as my y, when my time is 2, which is pretty much my x in this situation. Okay? So m of 2 is going to be 35 over 4 times 2 plus 5. All right, well, 2 goes into 4 twice. Half of 35 is 17.5 plus 5, which is 22.5. That's m of 2. And there we go. That was nice. So we come up with our equation, which is boxed right there in the green box. Or if I want, I don't know why that pops up occasionally. We can use this equation here. It's the same deal. This is the same as this. And then, oh, by the way, you better put this down. They do not ask you for a label, do they? No, but they want the temperature. If they had to ask you, that would be degrees Celsius. All right? They don't ask you, so don't put it unless they ask. All right, 3C. It says, write an expression for the second derivative of m. That's d2m over dt raised to the 2 in terms of m. Okay, so when I take the derivative of that, I should have an m of some variation in there. Then use that second derivative to determine whether the approximation from part B. Okay, remember, in part B, we came up with that m of 2 as an approximation. We said that was 22.5 degrees Celsius. Okay, this is the approximation from part B that they're talking about. Okay? So come up with a second derivative and use that second derivative to determine whether this approximation right here is an underestimate or an overestimate for the actual value of M2. Okay, and then it says give a reason for your answer. All right, this is going to be good. I'm probably going to, when I'm done with this, explain a little bit more than I need to, but it's good, kids. It's good. Let's tackle the first task. Expression for the second derivative. Write that expression. Okay. Well, the first derivative, which is given to us right here, okay, dm dt is 1/4 40 minus m. Okay. If I need the second derivative, see what I need is d2m over dt2. That means I take the derivative of this, the first derivative. Constant, I'm going to leave it alone. The derivative of 40 goes to 0, minus the derivative of 1m is just 1, but anytime I take the derivative of a variable in a related rates type of problem, I have to write dm dt next to it. All right? Remember, they want this in terms of m. What I like about this problem is they kind of walk you through it, right? Write an expression for second derivative. And oh, by the way, we need some sort of m in there. There it is. Look at that. Let's clean this up. Let's make it look pretty, okay? Go back to our, well, first of all, let's go back to our pen. And then go back to that purple. Purpley. Okay, so it's 1/4. This ends up being negative 1. But I can't write, dm. It wants it in terms of m. What I'm going to substitute in for this is what dm dt is. This is dm dt. That's going to go in place right here. So it's times 1/4 40 minus m. Okay, there's your m coming into play in terms of m right there. So let's start simplifying this a little bit more. Negative 1 times 1/4 is negative 1/4. Negative 1/4 times a positive 1/4 is negative 1/16. And then we have this after it, 40 minus m. This is the second derivative of m right there. This is the first thing they wanted, for us to write the second derivative, and we just did it. Okay? Now, the second thing is based on the second derivative. Is it an overestimate or an underestimate? Okay, we are now officially right here. We've got to answer the second part. So is this 22.5 an overestimate or an underestimate? Well, if you did not look at part A, we had to graph. We had to graph something. Here's 5, okay? So at 0.5 is where we started. And they had us kind of graph that function. I guess it was a function of the derivative, but I don't have to use that one. Let's just use one in general. Okay, let's use one in general. Why not screw it? We'll use that. Why not? Yeah, kids, I said screw it. Okay, this is just for comparative sake. Okay, 0, 5. We got that point right here. Kind of slope field. It kind of went like this. Kind of went up like this. Something like that. Okay, and we figured out for 3b the line tangent right at this point here. So this is the line tangent we kind of came up with. It's a line that goes like this. It's a line tangent. That's why I draw a straight line. Okay, now we had to figure out at 2, m of 2. If this is m of t, this is t. When t is 2, we estimated at this point right here where t is 2. But the actual line, okay, the actual coordinate is actually right here below it. So since we are higher than the actual, right here was our 22.5. That's what we came up with in part B. But right here is lower. I don't know, maybe it's 20 or something. It's lower. So what we guessed was an overestimate. But they want us to use the second derivative to kind of explain it. Second derivative talks about concavity, children. That's right. That means it's either going to be concave down or concave up. this is always going to be concave down. How do I know that? If we look at the original problem, M is always less than 40. No, we're never going to have a negative temperature, okay? We are not going to have a negative temperature. Why? Because it's taken out of the refrigerator and put in hot water to be warmed. Okay, your refrigerator's at what, 40 degrees? That's Fahrenheit. Sorry for all you guys that aren't imperial, or maybe you are imperial, I don't know, whatever. English, imperial, metric, okay? But M is less than 40. What happens if I look right down here, okay, and this value of M is less than 40? I don't know, 20. Isn't 40 minus 20 a positive number? It's positive 20. And if I multiply that times a negative, it will become negative. So my second derivative will always be negative because this will always be less than 40. 40 minus a number less than 40 will always be positive. And I'm always going to multiply that times a negative number. So what I'm going to say is our estimate, our guess, is an overestimate. How come? Because this will always be concave down. Our second derivative is negative, so this will always be concave down. Okay, so at this point of contact, I'm always going to concave below it. All right, and that's the whole premise behind figuring out if something's an overestimate or an underestimate. So we have over, okay, I could have swore I hit that. Overestimate. Since, all right, since M of T, you know what, let's use a second derivative since D2 dt2 is less than 0. I was going to start writing words. This is therefore it is concave down at t equals 2. And you could write that a million different ways, and I was kind of thinking about different ways to write it, but that's simple. It's exactly what they're expecting. Now, some of you might say, well, what would it look like if it was an overestimate? Okay, what would it look like if it was an overestimate? Here you go. Here's 0.5, okay? Right there. Okay, we have some graph. Our line tangent looks like this in green. This is the line tangent we came up with. Okay, here's where 2 is. Because it's concave down, we have this one in red. It's concave down. That's why we're below what our estimate was. Here's our estimate. Here's the actual. E for estimates, A for actual. What happens if it was concave up instead of down? I'm going to do this in blue. If it was concave up at this point, it would go up like this. So the real point, well, this would be the actual. If it were concave up, if our second derivative was positive, then this would be actual, and this would be our estimate, and our estimate would be lower. It would be an underestimate. That's why it's important for a situation like this, and why they lead you to say, using the second derivative, determine whether your approximation is an overestimate or an underestimate. There we go. Oh, man. I don't mean to get excited. I knew this was going to happen. Separation of variables. Separable differential equations. I love it. D, use separation of variables to find an expression for M of t. The particular solution to the differential equation dm dt equals 1/4 40 minus m with the initial condition m of 0 is 5. Okay, this is your t, this is your m. If you want, this is like an x, this is like a y. But we're going to use t and m. Okay, so here we go. Let's do some math. All right. This might take a minute, but you know what? It's very doable math. Just be patient with it. All right, so I'm going to start by writing my dm over dt is 1/4 40 minus m. That's it. Okay? I've got to get my dm and m on the same side, and I want to get my dt and t on the same side. There are currently no t's, but that's all right. We can still do this. So what I'm going to do is I'm going to start by multiplying this side by 1/40 minus m. This cancels with this, and what I do to one side, I have to do to the other. Okay? Now, on the left side, I want to get rid of this dt. So I'm going to multiply this side by dt. This will cancel with here. And what I do to one side, I have to do to the other side. So let's write what we currently have together here. We have this on one side, 1/40 minus m dm, equal to this is on the other side, 1/4 dt. All right, I have got to integrate both sides. I integrate this side, and I integrate this side. Now, if you know your rules of derivatives, you should know your rules with integrals, especially with natural log. Okay, this left side becomes the natural log of 40 minus m, but it's negative. Okay, it will be negative. You can do u sub, that's fine, plus a constant. We'll call that constant 1 equals. This is even better, kids. This just becomes 1/4 t plus another constant. They might not be the same constants. That's why I call them constant 1 and constant 2. All right? And if you want, if you're, crazy enough with it, you can take this t and put it up here. You can say t/4. That's fine. I just like seeing, okay, the 1/4 stays 1/4 so far, and the t comes in. We can do that later. That's fine. The first step I need to do is I need to get those c's on the same side. We only want one c. Okay, and why are we solving for? Why do we put the plus c's? Because there are no bounds here. I'm not putting zeros there. I'm just drawing attention to them. Okay, there are no bounds, so I need to do a plus c. So let's subtract constant 1 from both sides, because I want to get my m alone. So on the left side, that's what I'm trying to get alone. Bye-bye. The negation of the ln of 40 minus m equals, now we'll call it t/4. Well, a constant minus another constant is still going to give you a constant. And now it's a different constant, constant 3. I don't know, maybe it's the same. I don't know. We only have one c now, so I'm not going to put it c1 or c2. It's just a constant. All right. At this point, I'm going to use my initial condition to solve for c. All right? Remember, whenever I come up with an equation, all right, they want me to come up with the initial, they call it initial, come up with an expression or an equation for m of t. So in my equation, our expression, I'm going to have an m, I'm going to have a t, but that means I need to figure out what the c is. Okay, and they give us an initial condition. When t is 0, m is 5. All right, let's go down here. I want this at t 0, m or m of t, either way, is 5. So let's put those in right now. The negation of the ln of 40 minus my m, which is 5, equals 0 for t/4 plus c. Okay, this is really, really nice and really easy. Okay, you extend this bad boy. Go up here. Now, 0 goes bye-bye, so this side, this is my constant. It equals the negation, or negative ln, of 40 minus 5, which is 35. That's it. Don't try and get fancy with it. You don't have a freaking calculator. So this value is going into C, right here. So let's rewrite this line and put my value in for C. So it's the negation of the ln of 40 minus m. Remember, we're rewriting this line here. Okay, I don't want to make that 35 anymore. Okay, I just changed it to 35 to solve for C. Equals t over 4 minus the ln of 35. Okay, here's where your C ended up going. So in order to get m alone, I've got to do opposite math. I've got to get rid of that natural log and the 40, whatever. I want to get m alone here, all right? So the first thing I think I'm going to do is I'm going to get rid of that negative on the left side. I don't like it. I don't like it one bit. So I'm going to multiply this side times -1, which means I got to multiply this whole side by -1. So now I've got the natural log of 40 minus m equals, okay, this gets distributed to both. So negative t over 4, and this becomes positive ln of 35. So plus ln of 35. All right, good, good, good. Now the fun part, kids. Get used to ln and e canceling each other out, because that's what's important right here. I'm going to make a base e to both of these entire sides. All right? And this is where things get extremely easy if you know your rules. These cancel, and we just end up with 40 minus m equals. What happens? What makes me add exponents together? Well, when I multiply similar bases together. That's a rule that you need to know, okay? Times e of the ln of 35, okay? If I were to multiply those together, I would still keep my base e, and I would add the exponents like I did in the previous step, okay? See, I added the exponents together. How did that happen? Well, I had to multiply common bases to add exponents. All right, and now the right side is even easier because e and ln cancel. Just like we cancel them right here, we still cancel them right here. So I end up with taking this times 35. So I've got 35 times e raised to the negative t over 4 equals 40 minus m. It's a lot of writing, but it's a lot of simple work, especially if you know your rules with natural logs and e's. All right, so let's, that blue. Let's subtract 40 from both sides. Let's put it over here because we're almost done. Okay, so now I got my negative m still, because these 40s cancel, equals 35 e to the negative t over 4 minus my 40. The only thing left is to get rid of that negative. So let's, purple, green, green. If I multiply this times -1, I got to multiply this whole side by -1. So now I have m, or in this case, m of t, equals, okay, this becomes a plus 40. I just negate that, negative 35 e to the negative t over 4. That was a lot of writing, but it was a lot of simple math. I tell my students something at the beginning of every year. You're going to be doing a lot of simple math. If I give you a sheet of paper and a pair of scissors, and I say, cut this paper in half, you do it, it takes 2 seconds. What was that, 7th grade math? But if I give you a stack of 35 to 100 sheets, say, pick them up individually and cut them in half. It's easy. You're just doing a lot of easy work. That's what this is. And some of you who are confused might say, it's not easy. Well, that's because you don't know your rules. If you knew your rules, it would be easy. Look where we started. This really is a thing of beauty, okay? And it all comes down to the formula or equation, m of t. They want the expression, which means they just want this part, which is fine. We're going to give them m of t equals negative 35e raised to the negative t over 4 plus 40. We're done. I will see you for pre-response question number 4. Bye-bye.
Don't forget to subscribe and ring that bell.